Bueno, buenos días. Creo que vamos a ser poquitos los que oigamos esta plática. Entonces acérquense para acá. Hay mucho espacio. Les recomiendo que tomen la segunda fila porque la primera, la mesa estorba para ver la parte baja de las diapositivas. Eh, bien, les cuento rápidamente, pero ya creo que la mayoría de los que están aquí lo saben. El profesor Gani, Rafiq Gani, fue mi supervisor en el doctorado en la Universidad Técnica de Dinamarca y él trabajó muchos años en la DTU. Después, cuando se retiró, bueno, vino, varias veces ha venido a México. No había tenido oportunidad de venir a la unidad. De hecho, él llegó el lunes en la tarde y el martes estuvo en Azcapotzalco, el miércoles en Iztapalapa y hoy jueves en la unidad Coajimalpa. Mañana sale para una conferencia de varios días en Puerto Vallarta, en un taller de Process System Engineering, que es parte de sus áreas de expertise. Entonces leeré una corta semblanza del doctor Gani y bueno, los dejaré con su presentación. Esta semblanza la publicamos en las mamparas, hicimos invitaciones por correo. Es un tema que en la unidad, en las carreras de ingeniería biológica, que es casi la única que tenemos, no está muy integrada, ¿no? Como en otras unidades en las carreras de ingeniería química, ingeniería en alimentos, ingeniería bioquímica. Sin embargo, creemos que es muy importante que podamos manejar estos temas. Entonces les cuento que el doctor Rafiq Gani se retiró a finales del 2017 como profesor eh, en el Departamento de Ingeniería Química y Bioquímica de la Universidad Técnica de Dinamarca. Él fue director, era exdirector y cofundador del Centro de Ingeniería de Procesos asistido por computadora, CAPEC por sus siglas en inglés. Ha publicado más de 491 artículos de revistas avaladas por pares académicos de alto impacto, la mayoría. Eh, ha publicado capítulos de libro y ha impartido más de 350 conferencias, seminarios, plenarias, conferencias magistrales, muchas internacionales. De hecho, era una pregunta que yo siempre me hacía: ¿por qué un profesor viaja tanto, no? Pero pues un profesor con cierta expertise es llamado de muchos lugares del mundo para, para poder escuchar, compartir el conocimiento. El profesor Gani es el exdirector de la revista Computers and Chemical Engineering. Fue editor de ella del 2009 al 2015 y ha sido editor de la serie de libros El Sevier del Computer Aided Chemical Engineering, del CASE, y actualmente se desempeña en los consejos consultivos editoriales de las revistas Computer and Chemical Engineering, Sustainable Production and Consumption, Process Engineering, BMC, Química. Rafik ha obtenido 3 títulos de doctor honoris causa de la Universidad Politécnica de Bucarest, la Universidad de Pannonia y la Universidad de Babies en Bolivia. Esperamos un día poderle otorgar uno nosotros, como la Universidad Autónoma Metropolitana. El profesor Gani es el expresidente de la EFCE, que es la Federación Europea de Ingeniería Química. Su par es el AIQE o el AICHE en Estados Unidos. Ha terminado su segundo mandato en 2017. Miembro de la Academia Danesa de Ciencias. Es un miembro del AIQE o del AICHE y un miembro del ICEM también. Fue galardonado con el premio AIQE CAS Division Computers and Chemical Engineering en 2015. Y en noviembre de 2015 el doctor Gani fue cofundador y director general de la compañía PECE for Speed, que brinda soluciones de ingeniería innovadoras, precisas y constantes, rápidas para clientes industriales. También es profesor visitante distinguido en la Universidad de Shengan, en China, y en la Universidad de Sichuan, en Beijing, China, y profesor visitante en la Universidad de Texas A&M. Sus intereses de investigación actuales continúan en el desarrollo y aplicación de métodos y herramientas asistidos por computadora para el modelado, estimación de propiedades, síntesis, diseño de procesos y productos e integración de herramientas de procesos con énfasis en energía, sostenibilidad y aplicaciones de un enfoque sistémico o de sistemas. Bien, quiero agradecer la presencia de Rafiq. Thank you, Rafiq, for coming to this campus. And now I will leave you to give us your talk, que quiere decir que algo así como tiempo para una nueva clase de métodos y herramientas asistidas por computadora para enfrentar los desafíos que tenemos enfrente, ¿no? Algo así. Entonces, sin más preámbulo, Rafiq, please.
Thank you for a very thorough introduction. It's a very great pleasure for me to come and visit this campus of UOM, and it looks like a very modern and new campus compared to the two previous ones that I've seen. But it's also a great pleasure for me to come and give this talk here. Thank you for the invitation. So as Mauricio said, I will talk about a class of methods that we feel one needs now in order to solve the problems we want to solve for now and future. And so I will point out that if we are happy with the tools that we have now, then we cannot do the things we want to do in future. Unfortunately, it's more modeling and computer-aided systems that I will talk about, and not too many practical applications. But whatever I'm talking about here can be applied for whether it's bio or chemical or pharmaceutical, any of those processes would be valid. And so first I will start with this definition of process systems engineering. What is process systems engineering? It is all about systematically being able to represent mathematically the problem and solving it using a systems approach. Whether we want to solve modeling problem, design problem, control problem, we would like to represent it mathematically, and we would like to find different ways to solve it. So one of the main role of process systems engineering is how to understand the system and represent it mathematically, and then try to find different ways to solve that problem. And solving that problem, gain understanding so that one can understand and find better solutions for the system. So it is this what I'm going to talk about mainly, which is this part here. So first let's see how one solves the problem normally. Almost all the processes that you come across, all the products that you come across are usually made by experiments. So you have a system, you do a lot of experiments on the system, and then after some time you find one experiment that satisfies all your requirements, and so you say, this is my product, or this is my process. So it works because you have all the chemicals, all the products that you get. But the question is it the best? Can somebody find a better solution? So that we cannot guarantee, because by this experimentation, it's not possible to say that this is the best solution. So what happens if we then say that this system, we will make a model for it, and then we will do, instead of doing the experiment, we will do the virtual experiment. Can we find a better solution? What we would say is that if the model is representing the system, at best you will find the same solution, but much faster. Because it takes a lot of time to do the experiment, you can do this virtual experiment much faster. And maybe you can look at more alternatives. But basically you will find a solution which is within this system. But what we want is new innovative solution that can go outside the system. And for that, we would need models that are predictive, that can extrapolate from that system. So unless we have those extrapolation predictive models, just making the model and doing a simulation is not going to give us the solution. It will just help us with the time and cost, but not the best solution. So we have to do something more to get the better solutions. So with that as the background, let's look at why we need the innovative and more sustainable solutions. So let's see whether it's chemical engineering or mechanical or biochemical or pharmaceutical, what we have, or the first step we do is we identify some resources, feedstock, and we convert this feedstock to our product. But in order to do this, we have to use energy, we have to use water, we have to use many other chemicals, utilities. And what is the effect of it? The effect of it is that we impact the environment, we cause global warming, we pollute the air, and we produce a lot of waste. So we can get our product we want, we can have the process, but the effect is this. And if we think of that, we take all the processes that we have on Earth and represent that with this factory here. So that represents all the processes, manufacturing systems on Earth, and we put all the resources we have in this factory. What we will get is about 25% conversion. So we can best get 25% of the resources into useful service. 75% is waste. That is the current situation. And if we continue like this, very soon we will not have any resources and we cannot get the product we want. So the processes we have, that have to be improved by more than 40% compared to the current in order for us to be sustainable. And so that is the question, how do we find the new innovative solutions that are much better than the current ones? And now we can see that what happens in a chemical or biochemical pharmaceutical processes, and where is the energy utility requirement coming from. So here is our manufacturing process. We put in our resources, we get our product, and at the same time we get unwanted product, which can be carbon dioxide, which can be other gases that go out. At the same time, in order for this process to run, we need power in the form of energy that will come from a power plant. And in the power plant, we put energy sources and we get the power, plus we get greenhouse gases like carbon dioxide and others. So whatever we want to make, we get our product, but we get a lot of unwanted gases and other products that go out. and that causes problem for our environment. And so that also is a problem, and we can see that this is a utility or energy requiring, demanding system, and this is a energy utility supplying system. So we need this supply in order to run this process. Now, can we reduce this emissions here? We can if instead of fossil fuel, we use solar, wind, nuclear, bio, and convert all of these resources into the power we want. And the advantage of these is that if we can use this one, then there will not be any emission. So one thing that we should be looking for is not just look at the process alone, but combine it with this and combine it with the energy sources, so the total emission that will happen will be zero or negative. And if we can do that, we can solve a lot of problems. So, and what you will see is that in order to get this kind of solutions, the tools, the methods that we have now is not possible to give us the solutions. We have to look at other tools. So what we want is new innovative solutions that are significantly better. So then the two questions can be asked. Can current simulators, methods, tools solve the problems we are interested in? Because people say that, oh, we have Aspen or we have Pro2 or HYSYS, we can solve all these problems. And do we need a new class of software tools that promote and support innovation? So we, as I've shown you in the previous slides, we want innovation. Can we get innovation from these current tools? And all of these tools that you see here are unit operation based. Well-known unit operation, distillation, reactor, heat exchanger, all of these. Okay? So let us see the current situation. For those who are in chemical engineering, you would know this as a process flow sheet. And if you know this process flow sheet, you can enter the details of this process flow sheet to any simulator and do a rigorous simulation. That means given a flow sheet, its details and its design, you can perform simulation, mass balance, energy balance, and it will give you all the information you need for that process. You can also do optimization and control. If you have a working simulation, you can do process integration, combine the heat exchangers, mass exchangers, and analyze. If you have a simulation, for all the streams, you know all the temperatures, compositions, you can calculate the cost and assess the life cycle assessment, factors, sustainability, all of these things. But in order to do this, you need external tools. The simulator is not giving you those. Okay? So this we already can do, and I think in the courses you take here, you learn how to do that also. So now let's have the same flow sheet here and ask this question, how to synthesize the flow sheet. If somebody has given us this flow sheet, then we can do all the things that I showed. But how do I get this flow sheet? Who will develop it for me? And how do I know that this is the best? We come back to the same question that somebody has done some experiments on others and came up with this flow sheet, and so we can do everything. But how do we know that this is the best? Or if we need some special models for the reactor, for the separation, how do we get those models if they are not in the simulator? Because we are making a totally new process, and if we make a totally new unit operation, how do we get the models? Or how do we design the equipment and operation? Because the simulator does not tell us what would be the number of stages in the distillation column, what would be the feed location, what would be the reactor temperature, pressure. It says, if you give me the reactor temperature, pressure, I can tell you what is the conversion, what will go out. But somebody has to give me that information. And how do I find those information? And the final, if there is a reactor, we need catalysts, enzymes, so on. If there is separation, that is difficult, we may need solvents. How do we find all of these things? If we give it to the simulator, then it's no problem. But how do we find them? And how do we know that is the best? So these are the questions, but obviously people have solved this. But what you will see is that the solution is trial and error and not very efficient. So what I say is that there is an inner loop and an outer loop. So what we have is this is the process and we can experiment with this. So if there is a reactor and we have 5 different catalysts, we can check which catalyst is the best. So then we put one catalyst, we perform the simulation, we see what is the objective function. If we are satisfied, then that catalyst is good. If it is not, we try again. So for every, whether we want to find catalyst or solvent or equipment design or even flow sheet, we have to do trial and error. And if we do trial and error, then it cannot be that we will get new innovative solution. We can get it accidentally, but not from a theoretical basis. So that's why flow sheet synthesis, process optimization, controller design, safety, all of these we can do currently in this form, but it can give us a solution, but not necessarily the order of magnitude improved solution. And if we are working with unit operations, then we know all the unit operations that are there, and we have to use them. So it cannot give us a better solution if we just have to work with the unit operations. So now we can see that if we can formulate these problems mathematically, then maybe we can find some solutions that will not require this inner loop and outer loop trial and error. So first we need to see that we are working with chemicals. So here is, for example, a chemical that we want to make. We need to know all the properties of this chemical. Then this chemical would be produced in a process. Then we need the model of the process. And this model of the property will be inserted into the model of the process. And that will be the process model together with the property models. And this is typically what the process simulator has. The process model with the property models. But if we want to do everything that I talked about, we need more models. We need to know how to operate this. So we need an operation model. We need to calculate the cost. So we need a cost model. Then we need to check whether from an environmental point of view it is good. So we need the environmental model. And we also need to check the sustainability. So we need sustainability model. All of these are extra models that we need to have together with the process simulator. That is still not enough, because once the product is made, and maybe the product is not a single chemical but more than one chemical, so we need to make a formulation model, how to mix the chemicals together to make our product, which is multi-component. And then after we have made all of this, will the product work? So if we have like this, our product is a paint, which is not one chemical but several chemicals together, does the paint work? We can put it on the wall and see if it works or not, but can we, before selling the product, know all the properties of that paint? Then we need a model for that paint, and then together will be the total model we want to solve. And only this kind of models can give us the overall solution that we are looking for. So let's see then how we will tackle this kind of problems. Because process systems engineering tell us whatever the problem is, if we can understand the system, we can find out ways to solve those problems. So first, there's not going to be too many equations, just a few. So this is the generic representation of the problem that I showed before. All these models in a generic way can be shown here. First, we want to have an objective function because we want to minimize the cost. We want to optimize the operation. We want to take into account environment and sustainability. We want to take the safety and hazards. So we can add as many terms as we like. So that's an objective function that we may want to minimize or maximize. Then we want to put some constraints on the process. We don't want to make any chemical, but we want to make the chemical at the highest purity that we require. So that's the process constraint. Then we have the process model, as I showed you. If we are going to find a process, we need to have a model for the process. And then the property, the chemicals that are handled, they need to have property. Then process variable constraints, like what can be the upper and lower bounds of the temperature, the pressure, all these things. Then the molecular structural constraints, that could be what is the catalyst, what is the solvent, can we define them in terms of chemical structures. And then finally, what kind of process connections, unit operation connections we will allow or not allow. So which means that if we have a system through which we can get all these equations and the models corresponding to it, we can solve any problem. The important feature in this problem is that you see the y variable. These are decision variables or binary integer variable. They can be 0 or 1. If it is 0, a catalyst is not used. If it is 1, a catalyst is used. Similarly, a reactor and things like that. X are the real variables. They give us the temperature, the pressure, the composition, and so on. So then together it forms a linear problem if all the equations are linear, a nonlinear problem if some of the equations are nonlinear, or a mixed integer with real variables and integer variables if we have both these. And that's the kind of problem we want to solve. But it actually is a generic problem because it's not just doing optimization, it can solve almost any process product engineering problems. So here we can see how we can solve almost any kind of problem. The 7 equations are here. We have the objective function. And now, just as an example, if we take only equations 4 and 6 and just solve that, then this will be giving us the properties of the product. If we have a solvent, what is the solubility of the solvent? If we have a pharmaceutical product, what is the biological activity of that pharmaceutical product? We can calculate these only with equations 4 and 6. If we want to optimize it, we add equation 1. Similarly, if we want to just optimize the process, but not even optimize the process, just do the simulation, we need equations 2 and 3. That allows us to do the simulation. But if we want to optimize, we add equation 1. If we want to find out the best process flow sheet, we add equation 7. And then if we want to solve all of it together, then we solve all the equations together. So you can see If we just do process simulation, it's equation 3. If we do optimization, it's equation 1, 2, 3. Product evaluation, 4, 6. Optimal product, 1, 4, 6, and so on. So then you can see that if you have just the simulator, what can you do? You can only solve one problem. What about all the other problems? A process simulator will not solve unless you do the iterative loop. Okay? So now we will see that this is the problem we have. How can we solve, how can we find very good, reliable, fast, efficient solution strategies? This problem can have as little as 7 equations and as many as millions of equations. The biggest problem we have solved is 1.5 million equations for a biorefinery, making only one product with 7 locations and 6 biomass feedstock. If we want to solve that problem, we can formulate this problem like this, and it will be about 1.5 million equations. So, and if we have that, it is not possible for any of us, including you, to write those equations during your study period and then solve the problem. You need computational tools. So, objective is wide range of problems can be solved, and since we are talking about new innovative solution, we are going to show that these solutions will be better than what we have currently. So let's say that currently we have this reference. And this can be any current process or a reference design that we have got for a new process. But we can pass through this test to see whether we can improve it further. So we have the reference. So, and we will take 3 sets of variables. One will be related to cost, another to environment, another to waste and resources. So what happens if we reduce the cost, reduce the carbon footprint, that is the environment, and reduce the waste? The effect is that we will make more profit, we will improve the environmental health, and we will have more resources. So here already what you can see is that if people say that in order to find better environmental solution, you have to pay for it. You don't have to if you can find solutions where the carbon footprint can be reduced, at the same time the cost will be reduced. So how can we do this? How can we reduce the cost, carbon footprint, waste? Compared to the reference, we have to reduce the energy consumption, we have to reduce the water consumption, we have to reduce the demand that the process has. Remember that our manufacturing process is demanding all the utilities, all the additions that need to be done. If we can reduce them, we will increase all our requirements. And what is the effect of this? If we are able to achieve this, the efficient system design and operation will be achieved, and we will have reduced demand. And this also can be visualized in this way, that the boundary is our reference. And each vertex of the boundary are each of these criteria that we want to use for comparison of the alternatives. And if any alternative that we generate are inside, then by definition these alternatives are better than our reference. And therefore we are able to find new innovative solution if we are able to achieve this. So we need a method that will do this for us. So what we have developed is a 3-stage method. The first stage is synthesis. What it means is that if we do not have a process flow sheet, we will solve the synthesis problem. If we have a process flow sheet, we can skip the synthesis and come here. If we have an existing process, that means it has the flow sheet, it has the details of the design, we will come here. But first, let's see the synthesis process. Entry data is we have a chemical, we have a feedstock, and we know how to convert that feedstock to some chemical we want, but what is the process? And is the feedstock we are using the best feedstock? All of these things we can study in the synthesis stage. So that one will give us the optimal processing route. Once we have the processing route, then we will complete the design of that processing route. We will analyze the process, find out where the weak points are. That means why is it costly? Why does it use more energy than required? Why is wasting some useful raw material? We will analyze this and set targets for improvement. And once we set targets for improvement, that means targets for improvement would be reduce the demand. And then once we have set the targets for improvement, then in the innovation stage, we will try to generate alternatives that match the targets. And if they match the target, by definition, we will find better alternatives than currently we have. And by definition, it will be more sustainable. Okay, so this guarantees us the new innovative solutions. Afterwards, we will see, does it give us the global optimal solution, or is it even necessary? So let's look at the synthesis problem. And we take the case, let's say that in the feed, we can have any example, but I'm just giving you a chemical example. We take methanol and acetic acid. If we put here methanol and acetic acid, we will get unreacted methanol, unreacted acetic acid, plus methyl acetate and water. So we will have 4 compounds coming out here. Now if we want to make a process flow sheet, we have to separate those 4 compounds into pure compounds. Pure methanol, pure acetic acid, pure methyl acetate, pure water. The reactants we will recycle back, and the products we will take out. How can we find that? We need to know for each of those chemicals and the binary mixtures of binary combinations of chemicals, ternary combinations of chemicals, what can be the corresponding separation process. So just as an example, we can take a distillation column as we know it, and we can say if we put a distillation column with this feed in here, we can get one product here and the other compounds here. That could be distillation. And this can work for 2 compounds, 3 compounds, 4 compounds. So it's not just one, it's many more than one. But because methanol and methyl acetate, water, acetic acid, they all form isotopes. So simple distillation columns cannot give us the pure products we want. So we can think of pressure swing distillation, a combination of 2 distillation columns, or solvent-based distillation that can give us the separations we want. The 2 pure products come out here. And we have a binary feed mixture that comes in here. So that is another alternative. And again, for different binary mixtures at different temperatures, pressures, this system will work. We could also take a membrane-based separation. We can take some adsorption. We can take some special distillation columns or absorption columns or extraction columns, and we can also take some, it's not a distillation column, but it's a column-based separation technique. So these are just some separation techniques. Now remember that in order to get the flow sheet after the reactor, we need at least 3 separation steps. That means at least 3 of them, they need to be arranged in such a way that we get all the 4 chemicals out. So how many combinations can we make? In principle, hundreds of combinations. But can we then check each of them with the simulator? How long will it take? And do we have the design of each of them? Because before we do the simulation, we need the design. So we do not have time for that. But we still want to get the solution. So here is an example, one way to combine. So we have a distillation, molecular sieve, pressure swing, and 2 distillation columns. Okay? And this guarantees us the product we want. Is it better than any other? And how many can we generate? In practice, we can, for this process, we have generated more than 300. In the literature, you can find only 4 or 5. So among the 300, these 4 and 5 are there, but which one is the best? So we can do some ranking to find out which of these generated flow sheets will require the minimum energy, will have the lowest carbon footprint, will have the best environmental things, will require least utilities, and so on. But we do not have time and the information to do the rigorous simulation. So one has to generate a new class of models that can do these things very, very fast. And we will see that afterwards. So without that, you have to do the process simulation or experiment. Okay? So let's say we have done this and we have come to a process flow sheet. But this is not the only way. We can do it also by what we call superstructure optimization. So the difference between this and this one is that this one is called generate and test. That we generate flow sheets and then we test each of them, not with rigorous models, but simple models. But we check all the possible flow sheets. So one of them has to be the best. Okay? But here, we do not have to look at all the possible flow sheets. We generate the mathematical model for the problem, and then through optimization, we find the best solution. How does this work? And this is very common problem also for biorefineries and others. So I will give the example as biorefinery. Let's say we have this 5 biomass. And we have identified that from this 5 biomass, we can make any of these products. That can be ethanol, succinic acid, lactic acid, all kinds of products. But which biomass should we use? Which product should we produce? One or more? That will give us the best profit and satisfy all our requirements. So then we have different processing steps. Let's say this is the pre-treatment. There are 6 alternatives, ways to do the pre-treatment. And then the hydrolysis, and then the fermentation, and then the separations. But in each step, we only have to use one technology. We cannot use more than one. So then by optimization, we want to find out which is the best processing route. And let's say this would be the processing route, that we can take this and this feed, go through this one, this, and then we end up with 2 products. We can have the single product or a blend of product, and that combination will satisfy all our requirements. So how do we solve this problem? As I said, this problem may require as little as 7 equations and as many as more than million. So we want help with the computer to formulate and solve this problem. So we have a tool called SuperO, that is superstructure optimization. and it's an interface. This interface will help the user to create this network. And once the network is created, the user selects what is happening inside each of this box. And that is done here. Once they select what is happening inside this box, from here, and there's a corresponding model library for each of these box operations, we will get the model. The model will have more variables than equations, so we will need to specify some variables. So we have a database that will help us to specify the variables. Those variables can be what is the composition of the feedstock, what is the price of the feedstock, what is the price of the utilities, all of these things. Once we give the data and the model, then we have the total structure. This program will write the GAMS code, that is the optimization code, and call GAMS the solver for the optimizer, and then we will get the solution. So the user has to define the network, select the models, and almost everything else the system will do. And so we can solve the problem very fast, and we can look at many alternatives. Okay, now let's say that we have got the flow sheet. And here is a simple example of a flow sheet where we use benzene and hydrogen, which comes with methane, to convert it into cyclohexane, and the product cyclohexane comes out. Benzene and hydrogen will be separated and recycled back. So if we have this flow sheet and the design, all the details that we need, temperature, pressure, conversion, number of stages, feed location, everything, we can perform the simulation. Once we have performed the simulation, we do the analysis. But we need special tools for that: economics, sustainability, life cycle, all these. And once we have done this, we identify where is the problem. So the problem could be here, that this separation, if we do not want any benzene here, will require a lot of energy. And if we have benzene here, what will be the problem? Because separation of cyclohexane from benzene is very difficult. They have almost the same properties except the structure, so separation is very difficult. So, so if we can use up all the benzene, then we will not have this separation problem. On the other hand, if we do not have benzene in here, we will have a lot of hydrogen together with the methane. So we will have to purge the methane, and some of the hydrogen will go out. Also, if we have benzene in here, some of the benzene will go out, and benzene is carcinogenic, so it will cause problems. And so we will recycle back. Because we are using hydrogen gas, we need compression. And that also can be very costly depending on the flow rate. So just by doing this analysis, we could find out that this is a problem, the concentration of benzene is a problem, and the energy required here and here is a problem. Then we have to find solutions for that. So one of the solutions could be that put excess hydrogen, so all the benzene is used up. Then we don't need the extra separation of benzene. But we do have the problem that hydrogen will go out here, and a lot of hydrogen will recycle, so the compressor cost will be high. But at least we have solved the benzene problem. Okay? Those things can be done only if we analyze and find out where the problems are and what could be the target. So then we will assign the targets and we will find new alternatives. So now coming back to this design, all the things that needs to be done here, we can see in terms of these 12 tasks. Tasks 1 to 3 is actually stage 1, where we find the processing route. Once we have found the processing route, we will do task 4, 5, 6, 7, 8, 9. And these are the design stage that we are talking about. We do the mass balance, then we do simple mass energy balance, then we do rigorous, then we do sizing costing, capital costing, analysis. And here we get the targets. And then once we get the targets, we do the innovation, which I will come back later. So, and then again you can see that if you have a simulator, you are only doing task 7. All the other tasks need to be done, and you need models, you need tools for them. And so here is a new developed tool called ProCFD. Afterwards, if there is time and another room, we can see the demonstration of this. So as I said, you need a lot of data to solve these problems, so we have a library of databases. Then we do not want to calculate the cost, the carbon footprint, the energy consumption with detailed simulation models. So we have special models that can tell us what is the energy consumption of a process or a process unit operation without doing detailed calculations. Then with these ones, we need these tools, which we call the synthesis tools. If we do not know the process flow sheet, we generate the process flow sheet. If we do not know the solvent, we generate the solvent. All of these things we do here. Then, if we are able to do all of these, we can then go to the process simulator, and here it can connect to other simulators, external simulators like Aspen Pro 2. This is our own simulator, and in principle any other simulators. And you don't have to, that is the user do not have to write the input file for these simulators. The program will do it for them. So you can think of, if you have done a process simulation, how much time it took you to make those input files before everything was ready. Here you will get it immediately. And once you have the simulations, then you need all these analysis tools. Okay? So that is the new kind of tool that we are talking about, and I will show you how it can be configured according to your requirements. So now we come to the third stage, that is the innovation stage. We have the target, and what we want is a new flow sheet, new process that is better than the current one. So in this way, we can think of that this is our flow sheet that we have found, our reference. Okay? What we will do is that this flow sheet we will break down into unit operations, and then the stages of the operation, then what we call simultaneous building blocks and phenomena. That means after this we cannot break it into any smaller pieces. This is the same as if you take a molecule, break it down into a group of atoms, and then you can go to protons and electrons and so on. But after a certain time you cannot break anymore. Okay? So that is what we have done. We have taken a process and broken down into all the phenomena that happens. And what is a phenomena? Phenomena is a heating, cooling, mass transfer, heat transfer. These are different phenomena. Once we have this phenomena, now we say that combine these phenomena together and try to find a flow sheet that matches all the requirements of this but is better than this. So we break it down, then we combine, and we find, let's say, this flow sheet. Now this flow sheet has less unit operations than this one. So from a material point of view it is better. From an energy point of view it will have to be better because it will have to satisfy the target. From an environmental point of view, everything. So if we can find this and many others, they are all in principle better than this one. And why do we think that we can find? Because once we have broken down into smaller pieces, if we recombine them, in principle we will find many solutions that other people cannot find. So you can think of that if I give you 4 molecules A, B, C, D and say make binary mixtures for me. How many binary mixtures can you make? There are 6 possible combinations. Okay? So if we work with the unit operations only here, which is the tools currently, then we can work out all the combinations and everybody can find out the solutions for them. But if we break down into lower than unit operations, then there are more combinations. So we have the molecules A, B, C, D. Instead of these molecules, if I just give you carbon, hydrogen, oxygen, 3 atoms, and say make molecules with a minimum 4 atoms and maximum 20 atoms, how many molecules can you generate? And then from them, how many binary mixtures can you make? That would be millions. So that shows that if we do the same thing here, we should be able to find new flow sheets that other people cannot find. So here is an example. It is actually the same process that we looked before. Methanol plus acetic acid gives us methyl acetate water. That's happening in the reaction. Eastman Kodak built this process in the 1960s because they didn't know how to make those separations more easier. The one I showed you is better than this. Okay? But some clever engineers at Eastman Kodak worried about it because there were problems in different parts of the flow sheet. There was too much energy here and there was loss of acetic acid from some of the streams with the product. So these were not good. And they started looking at it and came up with this solution, which I showed you, and even better than this one. That means all of this is in here, in one equipment. Now, how did they find out? They were clever engineers. They started analyzing and then ultimately came to this solution. They convinced the company to build the equipment and found out it works. But if we want a solution like this for another chemical process, how do we do that? Do we depend on some clever engineer for another 20 years to give us that? No. Can our method that I showed you give this? If it can, we have a way to get to these solutions. Okay? So another thing is that we said that, and if there is time during the demonstration, I will show you how we can get that. Okay? And we also talked about energy, that we have to reduce the energy demand of every process. Chemical process is characterized by high energy consumption. And within the chemical process, distillation, sorry, it's not here, let's say distillation is using the maximum energy. So of the chemical process, 80% of the energy is used by distillation. And what we can see is that even though you find distillation in almost all chemical processes, even biochemical processes, pharmaceutical processes, is it the best separation from an energy point of view? It turns out that if we look at this plot, where this is the purity of the product against the reboiler duty, as the purity of the product increases, the cost of the energy increases. Up to this point, point A, it looks like distillation is the best. You can do the separation at a very low energy cost. But when you want to go from this point A to point B, all the remaining energy is used to go from here to here. That cannot be very good. can we replace this part by some other means that does not require this energy? If we can, we have found a very good solution to do our separation. We still want to reach this product purity, but we use distillation up to here, and then we switch to something else. And here is an example of that. Here is the distillation column. We want to achieve 99.9% purity, but we go only up to 0.85 with distillation. And then we send it here, and now it is 85% A, 15% B. With the membrane, we do the opposite of what people are doing. We take B through the membrane. The more B we take out, the more A will be pure. And this will require very little energy. And then we would save a lot of energy in this part by using this scheme. It does not have to be membrane. It can also be adsorption. It can also be solvent-based separation, as long as we can find a way to replace distillation for this part. And this is a solution that people have not looked at, because people think that they have to replace the distillation totally. It's not that. You can use distillation up to here, because you cannot use membrane from any point to this one. It has a limitation of flux. Adsorption material needs to be regenerated, solvents need to be recovered. So if it is a small separation, then they become very feasible. Does this work? Here is a gas separation scheme. This is the optimal gas separation scheme you can find in many plants. If you just add a membrane unit here and a membrane unit here, you save 44% energy here, 37% energy here. Now you can think of, if you can do for all distillation columns that are operating, how much energy can you save? You can actually solve the global warming problem, because there are 44,000 distillation columns operating currently in USA alone. If you can give me the number for Mexico, we can then say how much we can save in Mexico, how much we can save in China, India, and all over the world. And then you can think of, can we find a better separation technique than distillation? It turns out at this moment we don't have, but we are using distillation all the way to point B. We do not need to use distillation all the way to point B. So also I can show a demonstration of how this can be calculated. So now let's see what kind of new software we can make to solve this kind of problems. So one thing we can say that when you also have your simulators, they have a lot of features that you don't need. You only need a small number of things, and all the other things you don't need. So can we customize, tailor-make? If somebody wants a specific thing, we can make it for them. So this is how we do it. We say, okay, there is a main interface. There are different tools, tools for synthesis, tools for design, tools for modeling. And within each of these tools, there are sub-tools. These are different let's say, software. And some of those tools can be a template for synthesis. We can make a molecular product. We can make a processing route. We can do economics calculation, safety, and distillation column design, reactor design. These are different templates. Okay? And then we have libraries of databases, of thermodynamic models, calculation routines, different modeling techniques, synthesis techniques, design techniques, and all of that. So if we have all of that in different forms, ready to be combined together, then we can say that if we want, let's say, a tool for process synthesis and design, we start with the template for synthesis. And there is two templates. One is synthesis of molecules, synthesis of processing routes. Since we want processing routes, we take this template, and then there are three ways to do it: heuristic, process group, superstructure. We take this. From here, we get the processing route. Then we go to the design template, which is based on unit operation, and then we go to distillation reactor and so on. So then it will give us, like this, all the tools and the corresponding associated methods and tools. We need to make a special tool for synthesis. And here is how it will work then. We have all these libraries. We want to develop a new tool, and then we find out what kind of tools from the library it needs, and then we find out what kind of components they are connected, and then we find out what kind of components they are connected, and once we connect them, we have a new software. And it's plug and play. Just like equipment, you plug and you use it. It is like that. You don't need any extra programming to do it. So here is an example of that in terms of the you have the simulator. What does the simulator have? Database, solver, model library, flowsheet representation system, thermal library. And then the database may include these things and so on. Okay? But as we have seen, is that able to solve all our problems? No, because it cannot generate a flow sheet. Okay? So it would need extra tools here. It does not have all the chemicals, so it needs extra tools there. It does not have all the models, it needs extra tools there. So that's an incomplete structure. In the way I showed before, we can complete it for any specific requirement. New models and so on. So the new class of software, first, I think you people know that very well, is the modeling tool. We don't want to spend all the time writing all the equations, testing and all of that. The human is able to define the modeling problem and give its characteristics, give the problem, but all this part the computer can do for us. And if the computer can do for us, we save a lot of time in modeling. And once we have the model object, we can use it for any purpose we want. And all these models then will be included in our model development tool. And here is the ProCFD that I showed before, that we want to do the synthesis, the simulation, design, innovation, all of that in here. That's how the interface will look like. And at stage 0, we define the problem. How do we define? We say we have 2 inlets, we have 4 outlets, and the inlets have these chemicals, and the outlets have some of these chemicals, and each of the specification for inlet and outlet we give. And that's all we have to give. What is coming in, what is going out that we would like. We would like to find the process that is the best. So then, in stage 1, we solve the synthesis problem. We collect the data, and if the user cannot give them, the software will generate the data about the chemicals, about the process, and then solve the synthesis problem. Once the synthesis problem is solved, then it will go to stage 2. It will do tasks 4 to 7. That is the simulation, then the performance, sizing, costing, economics, and then we'll do the sustainability analysis and identify the targets. And then once the target is done, it will go to stage 3, do the heat and mass integration, perform optimization, perform intensification as I showed. And then at the end, we have a process that satisfies all our requirements. It's interactive, and like that it goes. How long would you need to solve this? I don't want to give it for education, because totally a new process from zero. We just give, for example, propylene and propane and benzene, and we want to make cumene, and it will have a byproduct. All the way to the end, we can solve it in 1 hour. But if you give it to the students, they won't learn anything. Your design course is, what, 6 months? So that will be counterproductive. So, but it requires a lot of other things. So one is that we can see the range of chemicals that it needs to be able to handle. So these are chemicals that we can come across, just representation of those chemicals. Small molecules, refrigerants, solvents, small active ingredients, pharmaceutical drugs, then solvents, ionic liquids, polymers, oligomers, surfactants, lipids. Now, nobody has a process that will make all of these. Okay? If you're concentrating on these, then you need only these chemicals, these properties. If you're making these ones, then you need some special models. If you're making these ones, you need some special models and special data. So there's no point in putting all of them into one. The customer can say they only want these, and then we will plug in only those tools. So then each of these will require their own database, and then we have the database. This is the example of lipids. And also here I would say that if you're using Aspen or Pro2 or HYSYS, they have a lipids database, but they have a lot of mistakes in it. This is the most complete database that is there, with about 350 lipids, and if you need interaction parameters for the thermodynamic models, all of those are available here. And then the database, the chemicals then need to have the property models. Missing pure compound property can be generated here. Missing mixture property can be generated here. Mixing parameters can be estimated through this, and in the end we can have a property model, and that property model will be a component for any of the tools we want to develop. So in that way, almost on any organic chemical you have, whether it exists or not, we can predict the property. So with those property tools, up to now I've talked about process, but can we also do similar things for a chemical product, like a solvent or a lubricant blend or a gasoline blend, or maybe insect repellent lotion or a spray, hair spray, or a cream? Can we make these kind of things in the same way? So that tool here, ProCFD, computer-aided chemical product design, it will do this. How does it do it? First, what can it do? It can do single species design, single molecule like refrigerant, solvent, lubricant, it can do. Functional product design, a product has a function like a shoe polish or insect repellent, it can do those. Then formulation design, where you mix different compounds together, like if you have a gasoline and you want to add some additional compounds to make the gasoline much better so that the car will run longer, things like that can be done here. And you can also make devices like fuel cells and others. Each of these solutions will require their own database, their own solution techniques, their own property models, and then their own functions. So if we make insect repellent and we spray it on our skin for mosquitoes, how do we know it works? We need models to check that also. And then each of these will require the database have different kinds of chemicals. Solution methods have different kinds of methods. Property models have different kinds of property models. And these are different performance models. So evaporation rate is a very common one. If you spray the lotion on your skin, the objective of the solvent is to deliver the active ingredient on your skin and vaporize out. And that is the evaporation rate. If it vaporizes too fast, you will feel a little bit cold. And if it vaporizes too slow, it will be wet on your skin. So you can optimize that to make it perfect. So like that, and phase stability, it should not be solid liquid on your skin. So these things can be checked, and the product can be optimized. So all of these can be done just like in a process design, but you do product design. And then you can also do the optimization of the product design. You just like in the Super O, you write a optimization code to find the best processing route. Here you do an optimization code to find the best chemical formula or the best chemical molecular structure by optimization. So I will not go into details, but it has been structured and done. So finally, we can see what kind of problems we have solved with these kind of tools: commercial feasibility verification of any new processing idea. Companies can say, well, we are making this product, but we have seen in the market, if we can make chemical B, it will be quite good. How much will it cost, and will it be commercially feasible? So we can do this very fast and easy. And we have done that for quite a few companies already. Retrofit, they have a process, but it's not working efficiently. So we go in, we do the design stage, identify what the problem is, and then we find innovative solutions. So these are different synthesis of new processing routes. These are very applicable now for the pharma industry, for the biochemical, biorefinery. Resolve operability issues. Many industries have this problem. Provide reliable process simulation and analysis. Many industries want that. At the same time, industries are also asking us to give the customized software tool. So we don't want to waste a lot of time trying to build new ones. We just take the components and put together. So in the end, we have these questions. Can current simulators methods solve the problems we are interested in? Do we need a new class of software tools? I think you can guess what my answer would be. Here is no, because of this reason: process simulators, unit operations, we can very quickly find out all the sequences, all the combinations, and that will never give us the innovative solution we want. Need to do quickly and include emerging raw materials and products. Vital to include process intensification and hybrid technologies, because they will give us the new innovative solutions we want. Do we need new class of software? You can guess the answer. Problems emerge faster than commercial vendors can adopt. So we cannot wait for the Aspen and Pro2 and others to do these things, include these things for us. They will only include it if there is a market for it. So it is important that now I'm putting on the academic hat. When necessary, I put in the industrial hat, and I say that these have to come from academia. Academia have to take the lead again, because where did Aspen come from? From MIT. Where did Pro2 come from? From one of the universities in California. HISIS from Calgary, University of Calgary. So they all came from academia. After that, we let them take over, and we did not develop anything. And so we just depend on them. But now we have to take over, we have to develop. And so this is also what I would say to all of you. You have to think of what new tools can you develop that can help to solve the problem of the future. Okay? And I would be happy to collaborate on this. I think you need to make a network, not only group here, maybe the different campuses of UAM, and then maybe other countries. And together, if you develop these tools, then the commercial vendors will want to use them. But the industrial companies are already using. Okay, that's all for me. Thank you very much.
Thank you, Rafiq, for a very interesting talk. So we have time for a couple questions. So, ¿alguien tiene una pregunta? Tenemos un par de preguntas. Sí,
Thank you, Rafiq, for your presentation. I think I learned some new things that I was also thinking on how to do this innovation in computer-aided in process engineering. One more than question is, what is your opinion about, you show this three-stage methodology, and in the innovation methodology you said you have, for instance, you put that there is a reference about cost reduction or the impact on the environment, the waste, no?
Yeah.
So I think this is what we need in an industrial point of view. But nowadays there is a new concept, I think is not really new, this is this circular economy. But I think this is more focused into the economy and into the process. So can you say this is related, or
Sure.
what should be the advantage of using this kind of knowledge in the process system engineering?
Yes, and this is a very good question, and I'm not a big fan of circular economy, and I can tell you also why. I think in the financial sector, that is a very good idea. Money should be recirculated. It should not be kept somewhere. And the more money you circulate, the better. But from a process point of view, the process have to satisfy the conservation principles. And the conservation principles require the thermodynamic laws to be satisfied. And if you talk about perfect circular economy, then you're talking about a perfect reversible engine. And at this moment, we don't have a perfect reversible engine. I don't think we will ever have, because that will say the production of entropy is zero. So it is never possible. What will happen in a circular economy in this sense will be that we will have a vortex where the diameter is decreasing after every recycle, and then we come to a point where everything is zero. That means cannot be recovered or recycled anymore. I can give you examples. Some people showed me a very good example of circular economy, that they had collected all the waste paper, cardboard, clothes, and they made a carpet. Very good. So they didn't use the original material, they made this. So I asked, what will happen now if I throw away the carpet? What will you make with it? So every recycle, the amount of use will decrease and decrease. So what I think is one should look at it from my point of view, sustainable development is a better way, because sustainable development says that we are using some technology and it has a lifetime. And before that technology breaks down, we have to find a new one. And as long as we can do that, our survival is guaranteed because we will survive. A good example of these things is rubber. A long time ago, rubber was natural rubber, but we don't have all the natural rubber to make the tires for the car. So we discovered synthetic rubber. So these are things that before we find out what the weak point is, we find a new alternative that can help us to go forward. And if we can do like that, we will continue. Circular economy, from my point of view, is violating the principles based on which we develop all our things.
Okay, thank you. And just one, well, I don't know if it's a question or comment. I think this new idea of new software, if I understood, you are developing, or have you developed yet this ProCFD software that I think is going to be very useful in the sense, as you said, no? We are using several standalone tools, and if we have this possibility to have everything together, it's going to be very, very nice, not to reduce the work. And if you have developed, how are you going to distribute? Are you going to we have to pay, we have to, the academia are going to be in your list, what is going to happen?
If I put the academic hat, I say that at least whatever we develop from academia, I would like it to be used and further developed, so we would be happy to find ways to have free distribution with some constraints, okay?
Thank you.
But for industry, it's not free.
Thank you.
Otra pregunta? Another question? Robert?
Well, I would like to say thank you as well. Then you probably know that we have this biological engineering here in Huancojimalpa. And then we have these students that are trying to learn some aspects of the engineering process and some aspects or really huge aspects of our biology. And then we try to combine these two. It's kind of complex many of the times because as I see your presentation, you are talking about process systems engineering, about tools, about models, about probably most of the things we know already. We know how to model catalysis, we know how to model some molecules. But then when it comes to model the cell, then we have a couple of problems. I mean, we have still big issues to solve. Have you tried to work with cells? I mean, try to optimize cells, try to simulate and design, synthesize the cell?
That we have not done,
including,
but I know some other group who are doing computer-aided enzyme design, for example. And then the enzyme design is working in reactions where they want to find out the enzyme will work or not together with, let's say, the backbone of a chemical that goes into the human body and things like that. So there are different areas where at this moment the knowledge we have is not enough. We have to use data a lot. So we need to understand the system through the data, and then once we have that, we can work. But here is where we say also that it's not only my group should develop the tools, we have to develop together with others, like your group or your colleagues who want to do metabolic engineering or things like that. We can combine together and we can develop them.
Can I place another question?
Sure.
Yeah, okay. It's more about curiosity when you start building the models.
Yes.
And this is probably the question that many modeling people place. What about the parameters that you're using? I mean, of course you have a huge amount of data, and then some parameters are not available.
Yes.
What do you do with that? You're still doing this parameters analysis within the modeling process, synthesis process?
Well, there are two things there. First of all, what we have seen is more and more, if we want to expand the application, like in your areas, we do not have the models, the mechanistic models. So we need to use data, and if we use data, we have to estimate parameters. And there will always be missing parameters. So that's where the question comes, can we have a predictive model? A predictive model will not require some of those parameters, or can predict the missing parameters. We have already done those kind of things, and this work when we go from one scale to a lower scale. Because if we, for example, have a molecular model, and then we find out that some molecular parameter is missing, we can go to the atomic model and create the molecule, and then get its parameters from. Then the question is how accurate the atomic model is compared to the molecular model. But these are interesting things that we have to add. And the more we are able to add, the wider will be the application range. So data handling, parameter optimization, these are very hot topics that we have to be able to accommodate with our tools. But we don't want to waste too much time, so we need predictive techniques.
Thank you.
Okay. Otra pregunta. Sí, José, please.
Just a comment. Taking into account your example of the distillation tower, that after that you made an hybrid with the membrane process, separation with a membrane.
Yes.
Have you considered, taking into account the question of my colleague, this, of course, in some synthesis, enzymes work quite well. So in some parts they can be used as an hybrid system. Are these considered sometimes in your systems? Or
Yes, when we make our network, with in every network, for every step, how many alternatives are there, we search the literature, and we take all the known technologies, including somebody found an enzyme, somebody found a membrane, whatever, and then we see with all of these which combination is the best. So that, but it depends on whether we can have the data and we can collect that knowledge of the technology. Then we can include it. But by ourselves, we cannot generate that knowledge.
Well, I have many questions about this,
Okay.
but I guess that we're going to have plenty of time to talk about it and discuss. So, on the name of our university, I'm going to give you this a diploma for your presentation. And thanks you again for a very nice talk. Thank you very much, Rafiq. And so I have a present for the director, that is me. Thank you very much. Y gracias a todos por su interés y su participación. Agradecemos nuevamente a Rafiq por su presentación. Muchas gracias. Va a ser